Hello. In this video, we're going to go over how to solve this circuit using the Wye-Delta transformation. We're going to use the transformation to find the potential difference across this 30 ohm resistor right here. The reason why you would use the Wye-Delta transformation is because in some circuits, you might find yourself facing a complicated situation in which you wouldn't be able to simplify the circuit further using your everyday series and parallel resistors circuit equations. And that's why I use the Wye-Delta transformation to simplify the circuit in order to be able to use those circuit equations. So before we actually implement the Wye-Delta transformation, let's go over what it actually is and how you use it. So you might have been taught the Wye-Delta transformation using this circuit. And this circuit basically is a combination of the Y and the delta. And I'll show you how that is by decomposing this circuit. You can see that it is made up of two schematics, namely the delta right over here, that consists of three nodes, 1, 2, and 3, and also the Y, like so, that consists of 4 nodes, 1, 2, 3, and 4. And the shapes of these respective schematics is what gives rise to the names. This is the delta, and this is the Y. You can also note that you can redraw these schematics into equivalent representations known as pi t, and that also gives you the equivalent transformation, which is the pi t transformation. And you can see that by redrawing this circuit in this fashion. This is the pi, and this this is the t. Let me just highlight the shapes so that you can see it. That is delta, this is y, this is pi, and this is t. And use the Wye-Delta transformation to transform these circuit representations from either delta to y, or from y to delta, or equivalently from pi to t, or from t to pi. And the reason why you would do this is, as I stated earlier, sometimes you face these resistor combinations that can't really be simplified using your normal circuit equations. Therefore you apply a transformation to make it simpler. Now that we know what kind of shapes we need to transform your circuit to subcircuits, how do we really apply the Wye-Delta transformation? Well, that's where you get these circuit equations. Let me zoom out so you can see that. Well, these circuit equations are used when you try to simplify or you transform a delta subcircuit or circuit into a Y circuit. And when you go from delta to Y, you can apply these three resistors circuit equations similar to the series and parallel equations, but you simplify them as labeled. And you got to keep note of how you label the circuits. So over here you have the RA, RB, RC in the delta circuit, and you manipulate these circuit values to obtain R1, R2, and R3. You can see that you obtain R1 by using the product of RB and RC divided by the denominator of the sum of all of the resistor values in the delta formation. You can see that this sum actually repeats in all of the numerators, and the only thing that changes is the denominators, and the only thing that changes is the numerators. Similarly, you can convert from Y to delta using these three resistor equations. You'll note that these three resistor equations are different from these ones that are used to convert from delta to Y. So that's important to note. In these transformations, the numerator is the one that's pretty much the same across all the equations, which is different to the previous one where the denominators were the same. And you, again, have to pay attention to the labeling when you convert the transformations, because that's what's most important. Once you plug in the values, you can simply obtain the transformed version of the circuit. And while this might be a little bit confusing to you right now, I'm going to explain how to apply it in this circuit right over here. The first step in finding out how to apply the Wye-Delta transformation in the circuit is figuring out if you can identify either a pi t or a Wye-Delta. And that's what you can see over here. Well, before I actually show it to you, why don't you take a second and think about whether or not you can identify a pi or a t or Wye-Delta. So pause the video just for a second and try to think of it. Now that you've thought of it, I'm just going to show it to you. I'm sure you would have identified a t right over here, or equivalently, a y. So you can try to solve the circuit actually, and see if you can simplify further. But for most of you, I'm sure you will find that it becomes quite complicated, and transforming this circuit into a simple form will help you in simplifying the circuit even further. So now that we have identified a y or a t, we can apply the transformation to convert it into a delta, as we have seen before. And converting into a delta would potentially help us to simplify the circuit much more easily. From y to delta, we use these three equations. So let's just plug in the values after appropriately labeling the t subcircuit over here. So the first thing that you got to identify is what are the labels of these resistor values. So over here, we're going to convert from t to pi, and we have to label it accordingly. So over here, you'll notice that this is R1, this is R2, which is 15 ohms, and R3 is the 20 ohms. When we compare it to the pi subcircuit that we're trying to convert it to over here, you will notice that this resistor is RA, this resistor is RC, and this resistor is RB. Now that we've labeled our subcircuits accordingly, we can simply plug in the values into these three equations to solve it. So let's just go ahead and do that right now. So to find RA, it is the addition of the products of 10 to 15 plus 15 into 20 plus 20 into 10 divided by R1, which is 10. You will find that this gives you a value 65, which is the value of RA right over here, 65 ohms. If you want to find RB, it's a similar way, 10 into 15. You can notice that the numerator is the same across all of these equations, but this time it's divided by R2, which is, in this case, 15. You'll find that the value comes out to be 43.3 recurring, and that is the value of RB. To find RC, it is as follows. Divided by the value of R3, which in this case is 20. And you'll find that value to be 32.5 ohms. So now that we've found the respective values of RA, RB, and RC, we can convert this circuit into the simple form that we want it to be. So let me just copy this and paste it over here. And let's begin to convert the circuit. So this T turns into a delta. And that is as follows. We get a resistor over here. Let me just erase this and write it a little bit smaller. This is 30 ohms. We also got another resistor over here, and this is connected right over here. And that is our circuit. So you will notice that, let me just write in these values. This is 65 ohms, which is RA. RB is 43.3 ohms. And RC is 32.5 ohms. Now that we've redrawn it like so, you can notice that 65 and 25 are actually now in parallel. 40 and 32 are also now in parallel. And 30 and 43.3 recurring is also in parallel. So now that we've simplified the circuit, we can actually apply our normal everyday series and parallel circuit equations to simplify this further. And let me just do that over here. So 65 in parallel with 25, using your parallel simplification equations, would be 65 multiplied by 25 divided by the sum of 65 and 25. And that gives you about 18.1. Similarly, 40 and 32.5 would yield 17.9. 30 and 43.3 would yield about 17.7. These are approximate values. So now that we've simplified even further, let's go ahead and copy the circuit once again and look at what it looks like now. Essentially, it converts into a circuit that looks a little bit like this, but with the new values. So we found that 65 and 25 would give us 18.1 ohms. We found that 40 and 32.5 in parallel would give us 17.9 ohms. We found that 30 and 43.3 in parallel would give us 17.7 ohms. Again, we're trying to find this potential difference right over here. So we can see that 17.9 and 18.1 are in fact in parallel. So let's go and simplify that even further, because we can use our series resistor equations by simply adding these two together to find equivalent representation. So that turns out to be just about 36 ohms. Now we can use the fact that these two are in parallel again and simplify even further. So it's the product of 36 and 17.7 divided by the sum of 17.7 and 36. And you'll find that this comes out to be about 11.6 ohms. So now that we have simplified it even further, you can see that it turns out that this resistor just turns out to be about 11.6. And this is the circuit that it all boils down to, which is a rather simple circuit now that we have performed the transformation to make it here. So what do you do past this point? How do you find V? If you know it, then that's great. You can continue to listen. But if you don't know it, spend a little time figuring it out. So pause the video and try to think of it. If you've already thought of it, this is how you do it. So we know that 20 ohms and 11.6 ohm resistors are in series, and we know that since they're in series, the 100 volts, the voltage is shared between, in fact, these two resistors. And we're trying to find the potential difference across this resistor. So the way you find V is by multiplying 100 by the fraction 11.6 over 11.6 and 20. This multiplication would give you the potential difference across the 11.6 ohm resistor. And this comes out to be about 36 0.8 volts. About this much. I used approximate values, so you might get slightly different answers. And that is how you find the voltage V across this resistor using the Wye-Delta transformation.